Okay, I'm Masaki Sato, the University of Tokyo. Thank you for coming. This morning is the New York meeting on tropical cyclone global storm resolving analysis. This is the University of New York office event, and this morning you have 5 speakers. So as a first speaker, I will introduce the background of some of the this event. As I said, this office is University of Tokyo in the next to the Central Park and the middle area of New York. Okay, my talk is here is global storm resolving modeling approach for better understanding of future change in tropical cyclones. So this event is a two combination tropical cyclones characteristics, mainly the future change, and also I'm a modeler, very high resolution modeling. So we call it the global storm resolving model, or recently kilometer scale modeling. So such a high resolution model, how to discuss the future change of hurricanes and typhoons. This is the topic. So here's background. So this is multiple purposes. First is as a University of Tokyo New York office event. So this is a 3 days workshop, but unfortunately only first morning is online distributed for registered persons. So yeah, if you are interested in the other sessions, please contact us for more information. So actually, we have a 3-day meeting. And this is organized at the University of Tokyo and the New York University in the New York area. I believe Columbia University and Stony Brook University, and maybe City College of New York will be a new partner of the University of Tokyo. So, and also this meeting is hosted by our own project. We call it International Quad to Co-Project on Global Storm Resolving Analysis. I show in next slide, it's a collaboration with different countries. And the topics of discussion is future change, future projection tropical cyclones, and intercomparison of global storm resolving models and tropical cyclone risk management. This is the topics of the discussion, but throughout 3 days communication, we want to focus more on these topics. Okay, this is a background. This is a brief introduction of the International Quad to Co-Project on Global Storm Resolving Analysis. This is Japanese fund from JSPS for 5 years. So we are basically academic field of Japan, Germany, United Kingdom, and United States, and collaboration with the projects. So you may know the global storm resolving model kilometer scale is now widely used in the many institutes in the world. So we have international collaborations, and there's a future discussion like a WCRP, and even in the Earth Visual Engine, like a Berlin Summit is one of the direction we are considering contributing for these activities. So the future change of the extreme events, tropical cyclone, is one of the topics most interesting in this active class. Okay, this is a background study. So in my talk, we are modelers, global storm resolving models. We have been doing the severe researches for this using this model for the future projection of the tropical cyclones. This talk is just kind of introduction of our previous research and some consideration for the use of high resolution. So the kilometer scale model is the model in the mesh, something like an order kilometer, and doesn't use cumulus parameterization, just on the direct microphysics scheme is used. And we have developed NICAM, non-hydrocyclocyclic atoms model, for about 20 years. But recently, many model groups have developed these linear models. So in a previous study, I think 3 topics are important for this discussion. First, we show the total cycle change in future projection. And the next is a change in convector mass flux. And the recent experiments sees and for the topical cycle genesis. Okay, briefly, NICAM. I will introduce NICAM. NICAM has been developed around 2000, and the first 3.5 kilometer simulation is run in using Earth Simulator 2004. And the current activity is using Fugak machine. And Daisuke Takaska did a longer simulation, and the very large ensemble simulation have been conducted, and the very high resolution simulated. And the international collaboration is also going on, Diamond Project, WCRP, Digital Earth, and our project. Okay, so future projection of tropical cyclone. This is one typical, important study generally referred to. So this is the MRI, Meteor Research Institute people's result with relatively close resolutions, I think 60 kilometer simulation MRI model. And they did to get a reliable projection, they did a 6,000 year simulations. So they did a kind of current and future simulation and 100 member ensembles, and using different types of SSD patterns. So this is a number of cyclones. This is probability distribution. So the observation and control current simulation and future in general. This is PDF of the memory ensemble. So generally reduction of DC numbers. And the horizontal distribution, this is a comparison observation current. So they have a good skill of reproducing the horizontal distribution. They change it, exchange it. So they get this kind of distribution, kind of the forward shift in the Western North Pacific, and also in the Atlantic, and very fewer in the lower latitude. So generally, typical 1,000 simulation, in this case, 6,000 year simulations conducted for getting robust tropical cyclone change. So yeah, the question is, robust kilometer scale model should do the similar experiments, 6,000 or 1,000. Yeah, this is one goal, but we want to discuss currently. It's almost impossible or marginally, whether we can possible or not. So that's one topic. So we have done, in contrast, we have done this kind of approach. 2017, that we discussed the tropical cyclone size structure change. What we did is using 14 kilometer. It's not a kilometer scale, but NICAM. We generally use this kind of force resumption. And 30 years simulation for present and future, just one member, not ensemble. But so yeah, we did some similar analysis, but we focus on more mechanism. So we want to study how the size or internal structure changes. So at this time, we did a AMI type 30-year simulation. After that, Kodama-san, Chihiro Kodama did a high-resolution simulation. We did a kind of two types of simulation, but typically multi-decadal simulation. So in this type of simulation, we did a MRI methodology using SSD current simulation, current data, and future data to plus simple multi-model average SST pattern. So just a simple one typical SST distribution. So this is the idea, the current simulation and the future simulations. So we may call this a time slice type experiment for this one. So this is the results, observation and control simulation. You may see various similarities. This is a bias and future change here. So just only one simulation, we have some similarity that MRI result. This is kind of north-eastward shift and the reduction in the areas. 14 kilometers is not so good to observe in speed, but the internal structure can be marginally reduced. We have an IO structure. So this is one important result is we obtain the internal structure change. Say we have a widening of the IOs and higher up. So the typical result, this is more detailed analysis, wind speed. So important thing is we are categorized in the intensity category 5 to category 1 to cyclone. If we fix the similar intensity type, then we can stratify the wind profile. Then for the stronger TC, this is a change. The winds are intensifies outward, and this means wind areas widen. So if we talk about the change in tropical cyclone, we don't care about the shift of the intensity change and the overall change. So we think it's important to categorize each intensity, how each intensity is the change is occurred. So these three categories, the higher wind speed becomes stronger in the outer area. So schematically, the IOs becomes more widening, means more taller and wider. So this horizontal scale becomes wider. So this is the reason for the widening of the tropical cyclone. So this is a typical one of our result using global storm result analysis. Global storm result model can capture kind of mesoscale structure, and we can analyze the mechanisms in the change of the meteorological field related to convective properties, MCS and IO structure. Okay, for the tropical cyclones, the future change, as you may know, the topography becomes higher, and the increased water vapor increases latent heat and cloud height and precipitation. So generally accepted for future change, precipitation is more enhanced. So intensified vigorous for each DC. So the deepening of central pressure and reflecting maximum speeds are also expected. And also, if this is additional part, increasing the size of TCs in number. So future change in number, this is an issue. You may have your own theory for reduction of TC. I have my own theory, so I want to advertise my theory. So please put your mind. So based on this intensification of each TC, we say, this is my paper in 2015, the constraint of the future change TC. So the basic idea is, Marat, your paper. So if you think about everything is TC, if you increase the SST, TC number decreases. This is because each TC becomes more vigorous, but the energy constraint, the total energy output is constrained. So if one PC becomes more latent heat release, then the total radiative cooling is fixed or slightly increased. So if you divide the total relative cooling divided the 1 TC latent heat, the number should be decreased. So this is my basic idea of the reduction. But to apply this to the real atmosphere, how much TC contribute the convective mass flux? We calculate this one. So here is the present mass flux, and this is future mass flux. We calculate the tropical cyclone contribution mass flux, like tropical cyclone area from center of 500 kilometers, and calculate the mass flux 1 meter per second. So we can, this percentage. So this percentage, if this the question is this percentage will increase or decrease. This is one question. So we put this is ratio R. So if this ratio doesn't change so much, the number of tropical cyclone, this is mass flux. Mass flux should be decreased because of weakened circulation. And 1 TC is more vigorous, so number should be decreased. That's my result from our simulation. This is a table. Number actually decreases for two types of simulation. And mass flux actually increased for each TC. Total mass flux is decreased, and the ratio is, this is difficult to parameter. Sometimes slightly increase, sometimes not change, but not changing. So this effect affected the reduction number. So this, please remember this result for basis for the discussion. Okay, almost time. I want go to the last part, seas. Yamada analyzed tropical cyclone seas, and this is also 14-kilometer model results, and this type of 11-year simulation, this is part of high-resolution simulation. So we calculated the tropical cyclone number as a multiplication of the seed and the survival rate. So we calculate the different types of model, and the seeds generally decrease, but survival rate also decreases in some models. So not only seed, survival rate effect is important for reduction of TC. This is my conclusion of the high-resolution analysis. But the TCCs, we analyze in the realized data current situation, TCCs and the survival rate contribution. Survival rate is more affected by the large-scale environment, like a GPI or things. Cs is depends on definition. So I think a definition issue, maybe you are familiar with C's definition and maybe discussion. C is more related to large-scale vorticity field. So C is related to the where the vorticity is not existing, like this one. In this case, more in the Eastern Pacific, the most central region, and the African wave regions. And the survival rate is more like a Genesis potential index. So the C's, different C's is unclear, but global storm result may be used to track back its origin. So GFT group did this kind of analysis. So detailed analysis of convex clusters, MCS and TC is, I think, we needed to understand C's. So various types of topical distance may be important. And our results show the survival rates more related to large-scale circulation. It's also important for projection. So this issue, I think, is a return back to the traditional problem TC, how TC genesis related to the large-scale field and the disturbance. So the classical paper to know, the relation of the genesis and types of large-scale circulation is, I think, is related to this kind of issue. Okay, I want to summarize. The global storm reserve model is the ideal model for projection of TCs, modulation of TC by large-scale circulation internal structure of TCs. So we can discuss both intensity and track feedback changes. But ideally, we need a 1,000 years ensemble simulation to get robust data. But therefore, almost impossible because we estimate if our communities target one simulation year per day, we spend 1 day, we get 1 year. So we need 1,000 days to get 3 years. So it's almost possible or impossible. But think about it, we need at least 10 ensembles so we can reduce time 10. So it may be achievable to ensemble simulation. So global storm resolving can be used to analyze testing ideas mechanisms. So we can, if we have ideas of theory, we can test using this data. So in that case, we are using convective mass flux and relation to MCS and TC. This is what we are holding. But the TC projection, we are interested in a future projection. How TC will be 2015. This heavily depends on how large-scale fields changes. SSD pattern, El Nino. But how about the El Nino will be more likely in the future is uncertain. So this is very difficult problem. So I want to, this is a topic we want to discuss during this seminar. So Rhythmic 2 in the course resolution is a key, but this is a new production in April in Met Opera. So we meteorologists want to see every new opera. So that's my talk. Thank you very much. So I asked you this morning, every people speak about 20 minutes and there are minutes discussion. So any comments? Questions?
I have questions about the number of the stones going to decreasing, and your argument is about energy balance, like the total energy conserved. What do you think about how to apply that idea to answer the number of the stones that has been more or less balanced throughout time? And also whether we are really in the Earth's environment, whether we reach that maximum or not. Because if we haven't reached that maximum, it doesn't really mean we cannot continue having increasing numbers. Thank you.
Yeah, first question, the answer or La Nina is totally reflected this ratio, the ratio of total stone contribution total mass flux. Maybe in the ENSO cases, this R becomes large or La Nina becomes smaller. So the change in the circulation pattern reflects this parameter. So I think it's important how the circulation pattern determines the total cyclone contribution. So yeah, this is really key issue in my opinion. I did understand second part. Okay. Yeah. Any other questions?
Maybe more of a comment. So Kevin maybe can talk about this, but in Erie and also with the high-risk MIP new steering group, there are some experimental designs that people are thinking of. And some of this thinking has to do with optimizing the resources like you mentioned. Some of it also has to do with finding the most signal for the investment. So there could be some things that could be done that maybe don't require such large ensembles if we want to go to that extreme resolution, or else if we're not in Japan and with Japanese models, or if we're not Bjorn and NVIDIA, we might need to compromise a little bit. So maybe Kevin wants to comment on the types of more idealized experiments they're thinking about in high-res MIP.
I mean, so for high-res MIP V2, which is in the process of, we're trying to think about well, we have a proposed structure already for some of those simulations. And what we're kind of trying to do is what I would argue right now is a blend of all of these things for V2 to try to think about, okay, what would in the future, maybe 5 years down the line, what can we be doing? So some of the more idealized approaches that Pierluigi is mentioning is that, so we've thought about, of course, you can do future projections with high-res MIP, similar to high-res MIP V1, which are, fully coupled. Those require oftentimes a lot of ensembles and are very costly. And so one of the ways around this is we've been thinking about, in addition to those, can we do some idealized warming? So similar to the US CLIBAR, which probably some people remember from 10+ years ago, in which we did the idealized 2-degree warming everywhere. But this is more coming up with kind of following the approach of the IPCC AR6. And can we come up with warming levels? So a 2-degree warmer world, a 3-degree warmer world, and can we add that to an existing, these would be prescribed SST runs in this case. Could we add that to historical runs in order to kind of come up with what the future would look like with a more idealized global warming fingerprint? And that's one way because you can do that in clever ways if the signal is constant, so maybe you don't need as many ensembles. The other approach just to mention is that we are trying in high-res MIP V2 to make the connection to experiments like Diamond, and trying to identify a specific year, maybe it's 2022, maybe it's 2023, in which you are running both at the global cloud resolving scale for a year or 6 months, whatever it might be, as well as running ensembles of your high resolution climate model, which might not be global cloud resolving at the time, for the same time period with the same boundary conditions to start to explore, right, some of that sensitivity as well. And so I just finished with saying that the high-res MIP, so the protocol for high-res MIP 2 is still kind of being flushed out within the next couple of months. But there should be probably a paper submitted that will be publicly available to all of the community, I would say sometime by the end of the spring. And so this will be out in advance of CNIP 7 protocol, which is similar to how it was done last time, part because we know modeling groups have some resources on computers now in advance to kind of CNIP 7 runs. So that kind of answers a little bit what the part of it.
Thank you. You might have a clever approach. Yes. Any other questions?
Hey, thanks. Can you go back to the slide where you had the change in mass flux and then the attribution of mass flux change to TC? The one with the figure. Oh yeah, no, sorry, you were there. Yeah, thanks. So looking at panel C, and just thinking about overall changes in mass flux in theory, do you think maybe it's possible it's just this isn't far enough out in time to really see a more uniform signal, or I'd love to hear more.
Yes, this is a mass flux change in the not only TC total mass flux. So this is zonal mean. So yeah, we don't see robust. We don't see robust slowing down. Just only southern hemisphere slowing down, and particularly lower levels. So the mass flux change is kind of marginal. So also this is maybe very dependent models. Radiation cooling profile determines this change. So it must be very dependent water vapor field. So I propose intercomparison of this kind of mass flux. It's important.
Thanks.
Okay, any other question? Okay. Okay, thank you very much. I finished my talk. So next talk, PM, please.
Hi, good morning. Well, first of all, Sam, thank you very much for organizing this. It's quite a meeting and you put a lot of work into this. It's very much appreciated. So I'll talk a little bit. So we heard about the global storage resolving models. I'll eventually get to it, but I'll talk about a project called Huracan, which is a binational project. So it's funded by both NERC in the UK and NSF here, and a number of people in the region are involved. The reason I wanted to talk about this is that I think, well, for many years in our work in the UK, we're looking at the complementarity of data generated by models to understand problems, particularly when we don't have such a strong observational foundation. So this project started asking the question of what is the risk of tropical cyclones for countries that traditionally don't receive tropical cyclones like the UK, but in general, mid to high latitude landfalls. And we are standing here in New York City, but the year 2012, so there was 12 years ago already, it seems like yesterday, Sandy here caused a major impact, massive losses. And we've had quite a few more of such events, but of course they're very rare. And so the question is, can such physically plausible models like we just saw help us to augment the sample size and better understand these risks? So this is the overall objectives: to understanding of the risks posed to, well, we had to say the British Isles and Western Europe because we had Brexit, we're not allowed to say Europe, and the Northeast United States. And so the two coasts, particularly the mid-latitude aspects of this, tropicals of cyclones of tropical origin. So we're talking about tropical cyclones retaining their tropical cyclone nature, and or anything that has undergone post-tropical. Ooh, it's happening. Strange thing happening. Okay, we're back. So our typical mental picture is that tropical cyclones live in the tropics, but that's not quite true, and I'll show you a few plots to try and convince you. But yes, so since the 1950s, we know that 3 to 5 these CTOs tracking with latitudes, and there are lots of reasons to believe they might pose a threat in the future. I will use this term CTOs to indicate tropical cyclone, anything that is a tropical cyclone. And well, we've had some very notable storms. I mentioned Sandy. Then at the time we were writing the proposal, so Henry and Ida were 2 interesting cases. One going straight up, and one taking a very big detour, but eventually still coming out in the same region. And on our side, we had Ophelia in 2017, and nearly made landfall in Ireland. And I keep losing my yes, which nearly made landfall in Ireland as a warm core tropical cyclone. And we've had a few other interesting ones that had unusual origins in northeast part of the North. And we had also some landfalls of things that again nearly came to the coastline of warm tropical cyclone. So they're not as unusual as you might think. So as I said, a number of people involved on both sides. So the project is divided into 4 work packages. So looking at different aspects of the life cycle. So we have the genesis aspect, we have the mature life cycle, so the work package 2, and this interaction with the is possibly the more innovative, more interesting, but couldn't exist without the other 2. And we have one on impacts, and the impacts part asks the question of whether or not these countries are ready to understand the impacts posed by the storms, because the impact model may be designed for just the one type of storm that we're normally used to receiving on our shores. And I'll argue that this is important. So first of all, this is a plot from Alex Baker's paper. So Alex is sitting in the back, will give a talk later today. So this is in his JGR paper looking at astronomical transition. So the counts since the, well, if you believe the reanalysis, at least since the 80s, or maybe if you look at AR5, you can go beyond. So looking at multiple reanalysis, there is strong inter-annual variability in these phenomena, but also there might be the hint of a trend, and this may follow theoretical considerations of what's going on with sea surface temperatures and also with the large scale environment, they might allow these phenomena to push further north. So this is one of the resources, and this is one of the questions: are we seeing more of these phenomena? And at the same time, are we see more of these phenomena impacting our regions? This is another plot from Alex's paper where he's looking at. So he's gone back into the reanalysis, looking at all these storms. So we have here. These are, so what Alex did was to classify the storm in terms of landfall in this part of the North Atlantic, or landfall and outfall. And he looked at what the storm track of such storms look like. So he's looked at the two storm tracks that pose a threat to this region or to this region. And then the next thing he's done is looked at how many are purely warm core, how many are purely cold core, and how many are hybrids. This is for that side, and this is for Europe. And you can see for Europe, the transition to cold core storm seems to be still predominant. And the reason this matters is that if you then look at the type of, if you break them down into those four categories and you look at the threat they pose at landfall, depending on what type of storm it is, the peak of the wind, in this case, is looking at maximum wind speed. The peak happens at a different time and with a different intensity. So this is important to know what arrives with what nature on our shores. So the ability to distinguish what is a purely warm core from what's a hybrid, from what's now transitioning to a traditional cold core extratropical storm is important. So anyway, what in Hurricane we want to do is to look at, as I said, this is from Reinhardsen's paper. He argues about all the chains of events, but the idea is in work package 1 to look at genesis, and particularly looking at unusual genesis, or at least that we know of unusual genesis. And this has to do with changes in the seasonality and the strength of the subtropical high, but also changes to the SSTs in the future. And Reinhardsen in his paper was showing these future projections of SSTs with favorable SSTs for tropical cyclogenesis going far more into the North Atlantic. And part 2 has to do with the expansion of the MDR. So again, conditions that would allow these storms to retain more of their tropical characteristics, far more north. And part 3 has to do with the interactions with the large-scale flow, particularly interaction with the jet, interaction between the tropical cyclones and the jet, and also the fact that as they move, these two things might come in and out of phase and might reinforce one another, or might actually impede storms going around and impacting in our part of the North Atlantic. So this whole survival around the anticyclone is a big question. Just to say that since we wrote the proposal, and this is what I was talking about before, this is Reinhardsen's paper showing in the future this progression of favorable SSTs to the Northeast North Atlantic. So he wrote this quite a while ago, and as years go by since that projection was made, what he was saying looks more and more plausible. And actually, since we wrote the proposal, we had 2 more seasons. And so after the year of Philia, we had another year that was really quite interesting. So we had Helene, we also had this one called Leslie. This is 2018. And then we had in 2022, we, of course, on this side, we had Fiona, that was really interesting. On our side, we had Danielle. And also we had this one in this idea of something that even doesn't go around the anticyclone anymore, but shoots straight up for Europe. We had Hermione that was generated here. And we had another one, Gaston, that also was generated in quite an unusual location. So we're seeing more and more, and actually some of this was all present in one picture in a single day in September of 2022. So all of these elements of new types of threats were present in a single day. We were developing, well, we're starting now on Hurricane. So just to say that for us, the record is extremely short and possibly very much unreliable. So if you look at, if you design that region as the region that is receiving the landfall, this is starting in 1851 going to 2022. I found 21. And if you, instead of starting 1851, you start in 1950, you find 14. So I would say probably before the 80s, much of this is not really very useful. And this is where models start to become useful. to complement the observations. On your side, there are plenty of storms, and possibly much more reliable, much more trustworthy. So what we did in Huracan, we decided we would use everything that is available to us. So in this plot, you have on this side at the top is coarse resolution, and down here is high resolution. So the GCRMs, so the sub 10 kilometer GCMs and convection permitting RCMs are down here. We came up with this concept of the augmentation factor. So how many more times the sample that we had in observations can we find? So we look at center scale reanalysis, maybe that's a factor of 100. And possibly we heard about high-res MIP, and now we're going into high-res MIP version 2. Again, we can find probably 100 times more such samples in the models. And then we have this whole huge resource, which are the seasonal predictions and the hindcasts from the operational centers. This is an augmentation factor of 1,000. And here, as we were hearing before, here we are quite limited in that these models are extremely expensive, but potentially using them in a clever way can also provide us with much larger sample size and trustworthy, sort of physically plausible. So I'll start showing you an example from these, and then I'll show you an example from these in terms of complementing the observational record with these model worlds. So this is for Ophelia. So this is a storm that happened in 2017, nearly made landfall in Ireland as a warm port storm. What Leo has done is to go back into these hindcasts from ECNWF and look at Ophelia, very many times augmented. So this is all the ones that he found that look like Ophelia. So we could study each one of those, and that could be seen as a new ensemble member. And so you have a nice spread, and where they make landfall, but also the consequences for the lysis are quite well spread. And then he looked at the cases in which the minimum pressure went under 980 hectopascal. So of course the track is much tighter, but we still have quite a few possible landfalls here in both Ireland and in the northern part of Great Britain. Possibly also here, the spread is a bit smaller than what we see up there, but where they are tight is on the Genesis side. So these are all, for one storm, these are all plausible scenarios that we can study, so we can use these. That's from one model. And this is what, and this is really important, this is what the intensification looks like. So if we look at all the matched tracks, this is now looking at, so the model is rerun every year. So it was rerun in 2017, 18, 19, and so on. Different colors show the model of each model version year. And you can see that in blue, there are some strange, so particularly here, there are some strange initial times, which then reflect a delay in intensification and also possibly not quite reaching the proper intensity. And this probably has to do with the data assimilation system over time. All the other years do fairly well. This is the same now, again, with this criterion that the minimum pressure needs to be under 918 hectopascal. And I would say, again, with the exception of that one particular year in which data assimilation seems suspicious, they all start very much close to observation. They all achieve the intensity that was actually measured. And then what happens after is, of course, much more difficult to interpret. Also, because if they make landfall at different locations, then they might start to fill. If they come to land much sooner than the original storm did, then these are the consequences. But this looks now promising in terms of studying Ophelia. We have already quite a large set. And we will continue to look at these in the future as these become more and more available. So that's one resource. And then the other thing Leo did was to look now at all the hindcasts, and he's not just looking at Ophelia, he's now looking at something that makes landfall in a particular location. So here are all the storms, and first of all, he's looking at all the storms that could be identified and had the storm already in the analysis. So at the start time, the vortex was already present, and then he developed. So you have a lot of genesis points here. And then, of course, they follow different routes. There's genesis in the Gulf, there's genesis on this side. There is even some high latitude genesis. And these are instead the ones in which the vortex was not present at initialization, so the model had to develop storm. So there were, of course, favorable conditions But these are different genesis points. This is more relying on the model physics than it is relying on the data simulation. So these are two classes of storms we're going to be studying. And also we are looking now at the seasonality. When do these things happen? So the various colors tell you what the season is. And you can see that these high latitude events have to do with the later part of the seasonal cycle. And on the bottom then, he's identified, again, with the focus on the EU landfall, he's identified sectors. So if you split them into things that were generated here, these are the tracks they follow. So this is sort of going around the anticyclone, and then we got our classic African genesis happening more sort of August to September. And then we have again, as I was saying before, these high latitude genesis events that all happen very, very late in the season, as we heard from Ryan Hartman. So that's already from the IFS system. This is a very rich system. And if you come to cases that happen more recently, like in 2022, the ensemble size is now 100. So that's really of high interest to be able to do that. So I'll move now to the next category. Now this more the models running in free mode without a sophisticated data simulation system, moving to sort of climate applications. So we heard about diamonds. So we had initially bursts of 40 days with models at 3 to 5 kilometer resolution worldwide. We now have this project NextGems, and Alex will talk later in the week about NextGems. Again, the same resolution, sort of on average 3 kilometer GCMs. There's only 2 of them, and they will run AMIP style 30-year experiments. Then we have the preparatory runs for the project ERI that was mentioned before. It's a European project that is a follower to Primavera high-res MIP. So where I've run a very small ensemble of 10 kilometers. And we also ran at the Met Office with Lorenzo Tomassini, the 5 kilometer model 6 times for 1 year. And this is where we're going. So we're going for full CMIP type of experiment starting 1850, going to 2100 at 10 kilometers in the atmosphere and 10 kilometers in the ocean. So that will be a huge resource. That has 4 GCMs that will provide us with lots of data. But for now, I'll show you some of the previews. I do have one slide about ERI. It's just to say that in coupling the atmosphere and the ocean at 10 kilometers, the fact that we have these, so these are eddy-rich simulations, we have very strong mixing in the ocean. We had already seen from NCAR that the internal variability, so this is the long simulation, 250 years, and it's showing the heat flux into the ocean on the vertical. And just what is important is the fact that if you band pass this, an eddy-rich model has much more internal variability than a model that parameterizes the eddies. And this is really important because one of the things we care about is not just climate change, but also decadal variability. We looked a lot at decadal variability of tropical cyclones, and these are foundations with 4 GCMs that will allow us to look into that kind of problem. But just as a preview, what does a 10-kilometer model look like in terms of the intensity of tropical cyclones? So we have here the Primavera results. So this is the in black observations. So this is the pressure-wind relationships for tropical cyclones. So in green are the 60-kilometer simulation we had in Primavera, and in blue are the 25 kilometers. So what in Primavera we called high resolution. And now this is the preview of ERI. So these are 3 different subdomains. You can see that the 10-kilometer is very, very, very close to observation. So that was a bit, when Kerry asked me a question about where we were going with the 10, I said, well, it's going to be a bit better, but nothing dramatic. I have to say that now I have to eat back my words because it looks a lot better than I had expected. And some of this may have to do with what we did with how frequently we call the radiation. And that was done because of MCSs. And so we're now running an experiment to sort it out. How much of that is due to this very high frequency updates of radiation. But that looks very good. And also in terms of intensification rates for pressure, it looks very close to observations. So that's also good news. It doesn't look as good if you look at intensification rate for wind. I'm not sure you're going to show this, Alex, in your comparison to NextGems. No. Yes, okay, all right. So, but the other thing, the really important thing, and again, that's where the model jumps as we go to 10 kilometers, is the latitude of maximum intensity. So I show this plot again. This is the pressure for each one of the tropical cyclones we have here.
And this is the latitude of, so this is telling us where these things achieve their maximum intensity. So first of all, at 100 kilometers, 60 kilometers, and 25 kilometers, we don't have the full range of intensities in terms of pressure, but also they seem to be achieving their maximum intensity at fairly high latitudes. And what changes at 10 kilometers, I have 3 ensemble members here, is that they seem to, first of all, develop a lot more. So they become much more intense, but also the latitude at which they become intense is now far more a tropical latitude. So it means they are spending much more of their lifetime in the tropics and releasing all that latent heat in the tropics, which then will interact with circulation. So these are the difference plots to the coarser models. And you can see again, this red says they spend much more of their lifetime in the tropics and are much more intense. So what we suspect was happening is that at the coarser resolutions, these storms, they start off as tropical cyclones, but they only achieve maximum intensity when they start to steal baroclinicity as they move into mid-latitudes. So that's not quite right in terms of simulating tropical cyclones, but it's certainly not good news if we're trying to simulate the extratropical transition and the frequency of things that will come to our shores. If these things are systematically interacting with the baroclinicity and there is a large number of them coming up, then we'll overestimate the risk, but at the same time, we'll see things that are weaker than they should be. So there will be a lot of them quite weak ones. We found a similar result in the models that Alex is looking at in NextGen. Some of the models in NextGen were run also at 10 kilometers. And so we do see a similar relationship. So as we go to 10 kilometers and beyond in terms of resolution, the latitude at which they achieve maximum intensity does change. And just to say that the other aspect of this is to understand what objects we're dealing with. So I have here the Ivy tracks, tropical cyclone storm tracks, and this is what the 10-kilometer model does. And you can see that you have these very elongated tracks in both the Pacific and North Atlantic. And also you have the typical thing we are criticized for. There are too many of these things in the South Atlantic. But if you use hard phase space filtering to remove anything that is not purely warm core, this is what the storm track looks like. And if you believe what IB tracks tells us is the purely TS category, now these two storm tracks look very similar to one another. So we've eliminated these bits and we've eliminated things that are not quite purely warm core. And then if you then plot the storm track of anything else, so this is the ET and SS category in IB tracks, and this is what we don't consider to be a purely tropical storm with a full warm core. So this is 2 of the things that come out of the hard phase space diagram. You can see that these correspond to the regions of strong baroclinicity. So these are the extratropical parts. So these are one very important component of CTOs, but this is basically what we want to study in hurricane. So these are the risks posed to our countries at these latitudes, but they are not purely warm core as these are. And I think it's very important the model can do this and to contrast what the model can do at this resolution versus what 25 or 50 kilometer model can do is really quite important for hurricane. Just to say, as I mentioned, we are going to the 5 kilometer simulations multi-year. Lorenzo thinks he can run 30-year simulations now at 5 kilometers. For now, he's run a number of times at 1 kilometer. We've tracked his 1-year simulation. This is the one that we would like to submit to the joint exercise. I've tracked it with track, and it's quite important to see these precursors again over Africa, and then quite long track, and then the consequences for Europe, for places like we have some examples that look very much like Fiona up here. And then we retrack with tempest extremes, and you can notice much harder, of course, for tempest extremes, which is designed to identify the warm core part of the life cycle to find these precursors. So maybe we need to learn how to rerun tempest extremes in one modality and another, and then restitch together so that we have a better comparison to track. But just to say this is important, this is last year, and there was a lot happening here. Possibly there is a lot more here that is not shown in IB tracks, but definitely there's a lot happening here, and lots of things did develop into tropical cyclones. Just to say that there are some very interesting cases. A lot of these do develop into quite severe storms. So again, for the fracture Europe, this is important. Just to say that as we go to the 5 kilometers, so this was the result. These are 2 years of the 10 kilometer, 5 kilometers deeper storms, but maybe in terms of wind, it's not quite there yet. But certainly there are much deeper storms at 5 kilometers than there are at 10. But both of them look quite credible in terms of the pressure-wind relationship. And I'll stop here. So just to say that we are looking into several data sources to understand the risks posed by these storms at high latitudes. We see the models are complementary to observations. The new skill at 10 kilometers is the ability to identify ETT and the proper risk of CTOs. And again, what the latitude and maximum intensities is part of that. At that resolution, intensification is certainly good for pressure, not yet for wind. Possibly we do need to go up to 5 kilometers for wind. And we have a number of case studies, really quite a nice number that we can use for storylines and then take them all the way to impact. All of these selections in terms of what type of threat they pose and how we then model the wind footprint and all that to do the impact studies. And the next steps is to expand all this to many, many more hindcasts from the AFS and also to the Erie simulations, which will offer us century-long simulations in itself. And I'll stop here.
So here, Luigi, in the slide that you were talking about where you saw the improvement in the intensity as a function of latitude. So how much of that do you think is just driven by the local scale dynamics within the storms versus have you looked at all in the steering flow in the tropics? Is the steering flow better represented so you actually get trajectories that keep them in the tropics versus moving them towards the
I haven't yet done that, but what I did do was to look at the components of the GPI. So to look at where the bad shear is and all that. And certainly, as you increase the resolution, all of those bad things become more contained. So you have nice corridors for these things to follow and develop into.
So I wonder also then, I mean, another part to look at would be the size of these storms, right? Because if they're generally bigger and more mushy or whatever you want to call it, right, that they might interact with the steering flow differently than they would if they're more compacted.
So this is something that Alex is looking into from Next Gems, and I think he'll show that one plot.
Yeah.
Yeah. So he's been looking at it. Yes.
Hi, I have a question about your hindcast experiments. I think those are really cool. Have you thought about like communicating those results? And, is the approach going to be like any hindcast track is sort of plausible and fair game? Or are you going to do some sort of like trying to get it, return period? Like it seems like a hard communication question. So I just wonder what the tackle be.
So
Thanks.
Leo will publish the results and also all the tracks. But this question of the physical plausibility is the important one. If we go to impact, we'll have all of these things. We need to say, okay, which ones are we going to select to go to very detailed impact studies? So Susanna is part of this effort, and Ted Shepard looking at all these causalities and all that. And we do need to filter it all down to a set that is really physically plausible, that is worth then projecting into all sorts of storm surge.
No pressure, Susanna.
Your city's careful.
Right. So I remember with High Gem, Lynn Sheffrey, they're actually finding for extratropical cyclones, storms were stronger than reanalysis. I wonder if you all have had discussions about, as you're moving forward with these CTOs, how you're going to interpret things and compare them.
I'm going to ask you to Alex, who has looked at the astrotropical cycles. I haven't. So maybe you want to answer that.
Sorry, but I am asking relevant to these transitional storms and just what you're going to compare against.
Yeah, it's a good question. I mean, it's a good question. We don't, I mean, the basic problem is we don't have a reference data set, right? And there are some things that the reanalyses have in common. So for example, just the number of ET events. But one thing they don't have in common is what proportion of those re-intensify against the analyses. And so, the relationship between how strong a tropical cyclone is and then what happens to it, whether it re-intensifies or not, is not consistent. So, I mean, yeah, it's difficult.
Yeah, so I was thinking, so, one thing is about the model viruses, is the Delta disease and the coronavirus. And I've been told that a higher resolution model can kind of mitigate the model errors. But I didn't see it in high resolution. So now you have
I-
10-kilometer ocean, I want to ask,
Yeah.
do you see?
So
improvement?
in some models, we see that improving. If you had to say that was a result of high MIP, absolutely not. I think the models still look pretty bad. Whether or not that will improve as we go to 1010, I don't know, because most people are at this moment finishing the spin up, and some people are running part of the control experiment, which is the one with the fixed anthropogenic gases. Very few people have started the historic one, so early days. But if I had to say that I believe that error will go away at 10 kilometers with parameterized convection, all that, I don't believe it. But we shall see. Maybe this is again where we do need to go to 2 or 3 kilometers and try to at least suppress the deep convection. But I have no idea what this interaction with the ocean will do for that.
Okay, thank you very much. Thank you. Then Adam, please.
Yeah, our process for doing this event. I didn't know I could take the subway to the University of Tokyo. Let's see. No problem. I upgraded the operating system recently, and now everything is slow. So the time it takes me to get okay, yeah. All right, should get it close enough. Okay, so this is I'm gonna try to do something a little different. I don't say it. Huh. Okay, how about that? I think it's perfect. Yeah, I was trying to log that one, but okay. So I'm trying to do something a little different than I would have normally done in the past. So let's see how it goes. And I have a lot of people have contributed to this. Jiang and Susanna probably the most, but I'll just try to get the other names in there. But I put this stuff together, and in the last couple of days, and so nobody else necessarily endorses my all my statements. So I'm going to try to synthesize a few different things our group has been thinking about, which are things that are familiar to this audience. I mean, papers that we've written stuff about tropical cyclones, but I try to put them together into a policy relevant story. Like, what do we really know that we could tell to the people actually living in the world, or specifically I'm going to talk about the United States today, about tropical cyclone hazard. So this is an attempt to think in terms of what I've been calling and others have been calling usable science, meaning science that connects to the outside world in a conscious way. So it's some sort of positions up front that when we talk to the outside world about our science, things that are based on multiple lines of evidence are the most certain. I think this is uncontroversial. IPCC thinks this way. If the models say something, and we also have a theory, that theoretical understanding behind it, and the observations are showing that it's happening, and we really believe it. Sometimes we don't have all those things, and we have much higher uncertainty. But when that's the case, it doesn't mean that we should assume that we don't have to worry about anything. If there's a bad outcome and a worse outcome, then it depends what decision we're trying to make. But a lot of times, maybe we should be worrying about the worst outcome, even though it might not happen. So that's just some philosophical prejudices, if you like. So here's the scenario that I'm trying to think about. I swear it's going to get to tropical cyclones imminently. So this is a scenario that I've written like as if it was imaginary, but in fact, it's already starting to happen in the United States. So insurers, companies that write insurance and reinsurance that enable people to get mortgages on their homes, start to pull out of high-risk states. Florida's a big one, also California with wildfires, et cetera. And then when that happens, what happens in the United States is that what often happens is the regulators tell the insurers they can't charge as much as they think they need to. They tell our losses are too high, we need to raise rates. And the people, insurance industry people, there's a few in the room, tell me later if I get it wrong. The regulators say you can't raise rates, the insurers say, okay, bye, we're not gonna write insurance here anymore. And then the state provides insurance that it subsidizes. But then what could happen, maybe this is getting to the scenario part, those state plans are funded not by the United States as a whole, but by the individual states like Florida. And then they don't really have that much money. So if they had a bunch of bad years, they'll go bankrupt. And no doubt, this is an easy prediction to make, they will appeal to the federal government for help. In the meantime, this is a threat to housing markets and infrastructure because everything depends on tax bases, everything local level depends on taxes, which depends on people living there and building homes and buying homes. And if they can't get mortgages, then that is in trouble. In the long term, or maybe even in the not so long term, the federal government in the United States has a huge liability, has a huge climate risk. Everybody's going to look to the government for help when it becomes hard to sustain living in high-risk places because the private sector, won't support it under the conditions the government requires. So, what advice can we give as scientists, not to the whole political situation, but just to how much has the hurricane risk or the hurricane hazard in a place like Florida actually changed already, and how much will it change in the near future? Because a lot of it depends on that. That's not the only factor, and so here's some articles that came out after Hurricane Ian about this that showed how that this is sort of beginning to happen. Just to say that I'm not making this up, this was something that's very real, even if it hasn't got to the full level that I'm describing here. So so the question is, we tend to frame things in terms of, well, intensity is doing this and frequency is doing this, and maybe the sea surface temperature pattern will look like this. But if we have to put it all together to give an assessment to somebody who actually has to make a decision, how will we do that? So I'm just trying to think through that and say how it relates to the science that we're doing. So here's some other considerations for Florida. Insurance people will tell you climate is not the only issue. There's lots of other problems with insurance in Florida, so I'm not going to talk about them, and I'm not an expert just to say that the business sort of and political situation is complicated. Florida doesn't just have a lot of hurricanes, it's also very low elevation. It's very flat. A lot of it is very close to sea level. A lot of the coast is porous limestone, which means that seawalls don't work very well because the water can go under them and come up. On the other hand, a lot of people like to live in Florida. Population has grown a lot. My aging parents are there right now. So that if you talk about risk, which includes exposure, the exposure has been going way up, and that's probably the biggest factor in the growing risk. But I'm going to talk about the hazard because that's what we're about here in this room. One more, my attempt to be socioeconomic for a minute. This is population growth. So this is, I got this off some webpage, but this is population growth as a percentage of the US total over time, going back to late 50s. So it's been going up, not if you could show in absolute terms, Florida's population has gone way up, but also even as a fraction of the US total, it's a lot. It used to be like 3% and now less than 3%, and now it's 6-7%. So it's grown over the late 20th, early 21st century. And this is the growth rate in percentage of Florida's number. So it was really high in the 70s and 80s, and it's lower now as a percentage. And this is, I just put it here, the time series Susanna made following Goldenberg's paper about the number of major hurricanes in Florida. I'm not saying there's a causal connection between these things, but just to say that there was pretty high growth rates during a time of low hurricane activity, and maybe that was helpful. Now it's been more active recently, the growth rate is lower. I'm not saying that caused it, but maybe there's some awareness. And this, for reference, is Hurricane Andrew, which was a big shock because it did a lot of damage and a lot of insured losses. Okay, so that's just setting the stage in Florida. So now some science. What do we know about climate change and tropical cyclones? These are some figures from the IPCC AR5. AR6 is similar, but didn't have as nice figures in my judgment. But I won't explain these. These are explaining different things about what we know about tropical cyclones with a measure of change here for these different measures and the uncertainties and the shading. But what do I think we know? I think we know the intensity is going up, and we know that because of not just models are doing it, but we have a theory for it, potential intensity theory, and there's a bunch of observational studies that, in my view, mostly support that. Rainfall, a little harder to observe, but very high confidence it's increasing just because it follows Clausius-Clapeyron arguments and everything, and the observations are at least consistent with it, and every model that I've heard of does that. So we're pretty sure about those things. Sea level rise is, makes the storm surge more damaging, even if the storm surge itself is the same, but the sea height starts from a higher point. So those are things we know. The changes in storm tracks, I probably won't talk about much, but Jonathan's going to talk about it, I don't know, tomorrow, I think. The poleward expansion and all that. I think those things we see in the observations maybe don't understand as well, but it's starting to come into focus. So those are some things we know. Then there's things we don't know. So Saki talked about frequency. This is a figure from a paper Jiang wrote a few years ago that's gotten a lot of press, but it's basically two versions of our model that have different sensitivities to humidity. And one, it's a downscaling statistical and then downscaling model, downscaling CMIT models. And so it either has an increasing frequency or a decreasing frequency globally, and we don't know how to choose which one. That's our simple model, but if you look at the high resolution models, there's also, a lot of them show decreases, but not all of them. And I don't think we have I don't want to say there's no theory, there's ideas. There's a lot of exciting research going on. Saki showed some of it. There's stuff about seeds from Princeton Group and others. And we wrote this review paper about it, but the main conclusion I would still argue is that when it comes to global frequency, we first of all don't see any clear change yet. It's a time series that just wiggles up and down. You can see it here. This is a little out of date, but not doing much of anything. And I think we still don't really know whether global frequency is going to go up or down. Maybe we know more regionally, though. Maybe global frequency isn't that important because regionally, if there's structure to climate change, if the sea surface temperature has a pattern and it changes some places more than others, then maybe we would actually be able to predict the local frequency better, or the regional frequency better than local. So let's talk about the Atlantic, since I started with Florida. The changes in the Atlantic are big. And so this is the number of Atlantic major hurricanes over time, with the smoothed version in red. So there's this big multi-decadal variability. This is the measure of the sea surface temperature field, the northern hemisphere SST minus the southern, I believe, what this is. Yeah. So it's northern. So SST and hurricanes very strongly correlated, not even more locally than globally. And there's now a lot of evidence. I've become convinced about this over the last few years. It's certainly still debated, but this is work from Amy Clements' group at Miami. Katika Balomo was one of her students, I think, at the time. Postdoc? Okay, sorry, postdoc. With Mark Kane and others, which basically show, so these are large, so the black is observed North Atlantic sea surface temperature. And this is going back to the 19th century. This is starting in 1920. And it's two different large ensembles that are being compared in the red. And what you see is that these large ensembles, the ensemble mean North Atlantic SST has some resemblance to the observed curve. And if it's the ensemble mean, it has to be a forced signal because the internal variability averages out pretty well in these large ensembles. And so they get this dip in the 70s and 80s, right? This was the time when Florida was growing really rapidly. There was not that many major hurricanes in the United States. And this dip seems to have been due, at least in these models, to aerosol induced cooling off the US and Europe. And the aerosols have now been cleaned up, and so it's bounced back, and there's also greenhouse warming. But the aerosol effect is very local and affects the relative SST. So that's, we now think, causing some of this, at least some, and maybe most of this big Atlantic change. Some people still argue it's some ocean circulation thing that's unforced, but, and that surely, is there in models if you look over longer times when the frequency is weak, but just to say, I don't think there's a good chance some of this Atlantic warming has been anthropogenic, although more aerosol and greenhouse gas over the last decades. And now what about the Pacific? This is the thing we've been excited about lately, and maybe Jiang's going to talk about it more. But anyhow, This is again, based on work of Clement and Seeger and Kane et al., but we've got excited about it. So if you look in the models, this is CMIP6 models projection of the sea surface temperature trend in the Pacific over the next 30 years. And it looks vaguely El Nino-like, as Masaki said, so it's warming more in the east than the west. And if Jiang downscales this with our model, using the model that has a frequency increase rather than a decrease, but the pattern is not sensitive to that, just the absolute value. So you see an increase in the Pacific and a decrease in the Atlantic. This is showing whole tropics, which is what you would sort of expect in an El Nino, very, very broadly speaking. And so this is consistent with downscaling this sea surface temperature pattern. But if you look at the, and this is from HiResNet, since I should show a little bit of global high resolution models. It's HiResNet models. These are coupled models that produce their own cyclones. So they show a somewhat different structure, but still somewhat El Nino-like warming over that 30 years future period. And tropical cyclones that also look kind of El Nino-like. The Atlantic is suppressed. The Pacific, especially the Central Pacific and Eastern are active. But the observations look sort of like the opposite of that over the last. So that was future projection. This is historical trend over the last 40 years, the satellite era, but it's La Nina-like with a cooling, an absolute cooling in the Eastern and Southeastern Pacific. And so a downscaling of, and the observed track density, sorry, the statistic I was showing for tropical cyclones was track density. The track density is decreasing in the Atlantic, decreasing, sorry, in the West Pacific over the last 40 years and increasing in the Atlantic, which would be consistent with a La Nina-like trend. And we have a recent paper about this that argues that this is, a big uncertainty. I mean, not just there's papers being written about the SST pattern effect and how this difference in the pattern of global warming and tropical sea surface temperature will affect the climate sensitivity, but we tried to argue it affects tropical cyclones and other hazards and risks, maybe even more in some sense in the near term. You could argue that it's natural variability. I mean, the Pacific is very noisy and has large internal variability, so maybe the trend over the last 40 years is just an accident, but it's not so easy to defend that. This is from, Jiang made this based on Seeger et al.'s 2019 paper. That's the one that convinced me anyway to be either concerned or excited about this, I guess, depending on how you look at it. But it's two measures of the Pacific sea surface temperature state. So an east-west index, which is like kind of like a typical El Nino metric on the x-axis, and a meridional gradient, which is another measure of the SST state that isn't typically used. But anyway, El Nino would be on the lower left and La Nina would be on the upper right, and the dots are trends and different individual ensemble members from CMIP. And there's different observational data sets, some diamonds here, so they disagree on the magnitude of this effect, but they all agree that the trend is La Nina-like. The models are clustered around 0, but leaning towards El Nino-like. And so there's some overlap of these two that says it's possible the observed trend is internal variability, but it's not, it doesn't look that likely, which suggests that the force response in the models could be wrong. That at least in the near term, that maybe the right response to global warming is La Nina-like instead of El Nino-like, and that would be bad for the Atlantic because the Atlantic has more storms. So to add all this up and try to get to, what can we actually say about this? I guess this is if I'm trying to do anything different here, it's just to put the pieces together here. So if we think the aerosol cooling drove the 70s and 80s low in Atlantic hurricane activity, then it doesn't really suggest that's going to continue because the aerosols can't get cleaned up that much more, probably. But it does mean that we're less likely to go back to that state. I mean, we could still do an internal variability, or the thermohaline circulation could shut down or something, but it suggests that, we maybe stay where we are if that was the only consideration. If forcing were the only consideration. The Pacific trends could reduce the risk in the Atlantic if the models are right, or if the models are wrong, and the recent history were to continue, they could increase the Atlantic risk. Of course, landfalling, tropical cyclone activity is highly random. Whatever the trends are basin-wide, it doesn't mean that what's going to happen at landfall. And global genesis trend is a wild card for sure. On the other hand, for Florida, the thing that the bottom line ultimately to me that's hard to get out of is the sea level rise. It's unstoppable. It's only a question how fast it happens. and tropical cyclone intensity trends probably too. So if I sort of consider all that, if I had to give advice to somebody who had to decide how much the hazard had gone up or not in the Atlantic, I would say it is probably higher than 50 years ago, especially compared to the 70s and 80s. Maybe not by that much yet. It's not like we're, Florida's getting hit by major hurricanes, constantly every year. Maybe it's not out of the range of natural variability. But in the long term, especially, things are definitely not good, even due to sea level rise alone. I think, if I ran the world, I would look for ways to discourage development, new development at least, on the coast. But this is just a personal view. This is just me, talking. Maybe it would make sense to have community syntheses or assessments on things like this. In other words, instead of just getting together and saying, what are the different things we know about tropical cyclones, and what's the confidence of which we know them, frequency, intensity, and so on, like the great Knudsen assessment of a couple of years ago. Maybe we should actually try to put it all together and give a sort of policy relevant summary of what we think the real hazard is. And in principle, that should be based on real risk modeling, which I didn't show you much of, but the kind of thing insurance does, where you have synthetic tracks and you actually do probabilities at places along the coast, and not just sort of talk about basic scale trends. But I'm not sure that at this level, thinking about climate change, that we would believe those details that much more anyway. So, I mean, methodologically, how to do a problem like this in a way that's decision relevant and scientifically responsible, I think is still, debatable. But anyway, that's what I wanted to say. I talked very fast, but maybe we could have some discussion about it. Thanks for your attention.
Thank you very much. Okay, any questions or comments?
Hi, Adam. One of the issues that I've had with a lot of thinking around this is in practice, when we think about your scenario at the start, the timescale of that scenario is 5 to 15 years, maybe, right? And that's with a lot of these companies and decision makers, that's the timescale in which it's not a global warming timescale. So I wonder, when you take into account the fact that do you think this is really a global warming problem?
Well, that's why I try to frame it in terms of, so I think this is I don't want to say it's a misconception, but I frame it in terms of what is the signal now?
Yeah.
I mean, we can ask what's now in the next 10 years. I think the science it takes to do that is still global warming science, because all we can predict is the force signal, right? I mean, unless you believe in decadal prediction, I mean, maybe there's a little bit of skill there, but probably not a lot. So really, if we're trying to say, how is today different than the last 50 years? We're doing the same thing as if we're going into 2100, we're just picking a different time frame in the model. I mean, it's an attribution exercise, but you're still looking at
the signal is
changes in
smaller,
risk.
right? That's the challenge, maybe.
It's small, yeah, it's smaller, sure, that's a challenge. On the other hand, the upside is we have observations for the period, I mean, though they're noisy. But yeah, I mean, absolutely. But I do think that, you used to hear, I mean, I've been going to insurance industry meetings for about a decade now, and you used to hear from people, oh, we don't have to think about this about global warming, because we write 1-year contracts, and this 2100 stuff is irrelevant to us. I think that was just always wrong, because even if you are just talking about 1 year, you still want to know how that year might be different than the last 50, or the average of the last 50 or the last 100. And the force signal is all that will tell you that. And to do that, you need the same kind of modeling exercises. So I'm not saying it's any easier than you said. I'm just saying those are the things to think about. And that's why I think in talking about all this uncertainty, I guess that's what, when I talk about usable science, that's what I think the difference is. It's not the exercise I'm suggesting we as a scientific community could do is not just to say, well, how can we make the models better so that we'll have an accurate prediction that we believe. That's a long-term project that isn't going to happen on this time scale. But instead to say, what do we know, what we don't know, and based on all of that, what is the risk? And the risk includes not just the sort of stochastic uncertainty of this could be a bad year, but also the things we don't know about the force signal. And so what do we think the probabilities are of the different You know, what I mean? Everything we know and we don't know is part of it, and so we have to be. I think the difference between what we often do is, as research scientists, is just that. I think this exercise involves focusing on the stuff we don't know, because it's as important as the stuff we do know, and even if we can't solve it.
I would also add, to your point about scenarios, I think putting a probability on it is great, but I think there's also an argument for if it's plausible at all, it's a scenario, right? And so considering that worst case without assigning any kind of probability, you know, being careful about it is also like a viable option to consider.
Yeah, and sometimes we won't be able to do probability.
Yeah.
I mean, if this is, you know, if the models are really wrong about the probability.
Yeah.
Like, I don't think we'll resolve that with any certainty in the next couple of years. So we have a multi-model ensemble that's here and some risk that reality is there. Like, what do? We can't like count ensemble members, you know, but we know something is. So yeah, absolutely.
Your leads?
So that was, in many ways, reinforcing all sorts of things I've been thinking about. So we are having all these discussions in theory, which scenario to run, because we cannot run every scenario. And there is a group saying, oh, we need to run the one that looks most realistic. But they're thinking about society and emissions, not thinking about the natural. And some people say, look, forget it. We need to run the one that gives us the strongest signal, given that very likely also the internal variability will be higher. But in so many ways, what you just said, actually, to me, seems to give a higher priority to storylines. We don't want to keep trying to guess what is the best future emission scenario. What we want is to cover all these things.
Yeah.
So we need to have a storyline on this.
Yeah.
If the tropical Pacific looks like this is what will happen to Atlantic hurricane.
Yes.
And if it looks like that, which is what currently the models say, but there is no reason to believe it.
Right.
Yes, there
Well,
will.
maybe some reason.
Yeah.
But
But particularly where we are right now, right? From what we know right now, we need to look at these different unfolding, right?
Right.
And so that would be a much higher priority to me than figuring out what the emission scenario.
Yeah, I mean, absolutely. I mean, you know, so JAG's leading 2 projects and Jimmy's working on it. On trying to do that, trying to do storylines. I mean, the trick with so I totally agree with everything you said. I guess, I mean, some considerations too are the time frame matters. I mean, these discussions about which emission scenario don't matter so much in 2030, but they matter a lot in 100. Yeah. And also the trick with storylines is like we don't assign a probability to them because we can't. But we have to believe that the probability is not 0, right? We have to believe it's big enough that we care. So that's always where the judgment call comes in. But I don't think we have any alternative for some of these issues.
Yes, I have a question. You said that in Pacific area is more active, PC means less active in Atlantic. You say such a seesaw pattern?
Well, okay. I mean, it's of course more complicated than that, but this is what Giant gets from downscaling. It's not exactly an ENSO pattern. This is probably closer to an ENSO pattern. So this is what high-risk gets, but it's also a different SST pattern. This is the 30-year trend in a bunch of high-risk models up to 2050, and this is the change in track density that they get. But in both cases, the Atlantic is first. I mean, what happens in the Pacific is a little more complicated because it obviously depends on both the downscaling method and what the actual SST pattern is, which is pretty different between those.
Do you see this in this observation?
No, these are models. So these are future projections. This is CMIT models, an average of a lot of them, and that's an average of, I don't know, half a dozen or something. So these are near future projection of trends. What's being plotted is a trend here.
So the observation doesn't show this kind of seesaw.
Observation looks like,
Yeah.
well, this is the trend over the last 40 years. So it's kind of seesaw. I mean, I'm not perfect, right? There's some complicated stuff here, but
You may say the even internal variability did not show this seesaw. The future projection maybe.
what I'm saying is this is the observed trends over the last 40 years, and it kind of does show us. not a perfect one, but.
On trend, not the interannual variability.
The interannual variability, okay, I don't have here the El Nino composites, there is some degree of that, so in El Nino, the Atlantic is suppressed, the Central Pacific is active. I mean, the West Pacific is a little more tricky because of the reason for the West. But yeah, it is some of it, but it's true that the trends, I mean, using El Nino and La Nina historical events as proxies for the trends is not perfectly accurate, because in these models, the trends, as James been showing, and I won't show those results, maybe she can show that they don't. They're and so events are not a perfect analog for the trends in either the models or the observation. That said, the reason I really like using ENSO as a reference is that it's something where we actually know what happens. We have an observed sample, and it gives us some grounding in, you know, how cyclones respond to trends. So some people think we shouldn't say El Nino like and La Nina like because it's not perfectly correct, but I still like it because I think it gives us a strong observational basis.
Any last question? You have.
Could that 40-year observational trend be driven by Asian aerosols?
Yeah, sure.
Could that 40-year trend be driven by Asian aerosols?
Oh, by Asian aerosols. It's possible. Yeah, I mean, for sure, some of this, I mean, so I did a sleight of hand, which nobody complained. What's that? Oh,
He has to have the even aerosol who has to be.
right, yeah, so absolutely, and some of this, so, okay, so Murakami says some of this is Asian aerosol, and some of this is surely Atlantic aerosols going away. So it's not to say that that's the whole, you know, that the P specific SST is the whole story, but. And so when we go to put them together, like, how do we, you know, I don't know, but there's, both those factors are there.
Okay, good.
Okay.
Thank you very much. Sit down, please.
Okay. Not that I want you all to see my email, but. Right, okay, so first I'd like to thank the organization for having us here. It's so amazing place with this beautiful view of Central Park. Second, I'd like to apologize for those who saw my talk at AMS or my second talk at AGU, because it's basically the same talk, so you guys can go have a walk. So this is a summary of a project that we have funded by NSF. Where we are looking at ENSO and tropical cyclones in the future. And apparently you have to have a C in the name to be part of this project. Christina or a C in the name. So what we want to know. So we want to know now how will ENSO tropical cyclone relationship change in the future, if it's going to change. Sure. And that can come from different aspects and different issues. So could be that ENSO is changing. Yeah. Could be that ENSO magnitude is changing, or diversity, it's a pattern again, or the frequency. Or could be the tropical cyclones are changing. And then that will also influence the relationship. Or could be then both the relationship between these two things are going to change in the future. So that's what we want to examine in this project. And we want to look at, we change the robust across different climate models, we change our dependent model biases. So we have in this hierarchy of model kind of approach. So we're looking at different types of models. So what I'm going to present you is the work that I have been leading on the look at the large scale fields on the CMIP6 models on that question. Chang has been doing the same with the downscaling of the CMIP6 models. I don't know if she's showing that here or not. And then We also have Christina Cotricola's group looking at different issues in high resolution models. I have a senior undergraduate, which is Sofia Di Pietro, who's doing her senior thesis on this question, look at the high-res MIP models. And then Christina Karen-Perry-Ju is looking at a lot in the ENSO question. So what Christina has shown is that the ENSO pattern and strength is very important to determine this tropical cyclone ENSO relationship. And when you look at different models, so here is our typical Eastern Pacific type of El Nino, and here is your Central Pacific type of El Nino. And then when she looked at CP5 models, there were models who had a strong ENSO diversity, means that they were doing a lot of Central Pacific El Nino, and in the historical, and pre-industrial runs. And there are some models that have a weak ENSO diversity, mainly they only do the Eastern Pacific. And then you have different, she also showed that the trends in SST in the CMIP5 models are different in this. If you have a El Nino climate model that does a lot of Central Pacific El Nino or no Central Pacific El Nino. So she came up with a way to quantify that ENSO diversity. And I'm not going to go into the details, but basically that's based on observations. So she looked at the EOFs of SSTs in the Pacific. And if you do the PCs, you see the spread of the different Central Pacific and Eastern Pacific. And what she came up with, you can fit like a parabola, and this alpha of the parabola is a good measure of one, how the presence of the flavors of El Nino, the Central Pacific is Eastern Pacific, and also the ENSO activity and symmetry of the models, and also how well the models are doing the ENSO feedbacks. She showed that in observations. And then she applied that to the CMIP5 models. And basically there were two group of models in CMIP5. There were the group A models that she showed that basically has a strong nonlinearity. This alpha is your nonlinearity. And there are some group of models that have a very weak nonlinearity. These are the models that do not have many Central Pacific events. So that was CMIP5. Then in this project now, we are doing this for CMIP6. And then we decided to classify the models in 3 categories. So in red, you have your range of this alpha parameter in observations, 2 different observations, because SST observations have all their uncertainty as well. And then if you look at the CMIP6 model, you have basically 3 groups. You have your green models here, as we call models A, that basically their ENSO diversity is more or less in the range of observations. Of course, there's a variability between those models as well. And then you have these gray models here, or B models, that basically they have a very weak ENSO diversity. So these models are not doing your Central Pacific El Nino at all. And then they have this other group of models here that are actually the other way. They do too many Central Pacific events. So they're always doing Central Pacific events instead of Eastern Pacific. So we are going to look at the tropical cyclone ENSO relationship in the large scale in these 3 group of models, the ones that have too much diversity, too little diversity, and about right, and see if we can say anything. But before that, we have to define what's an El Nino event and what's a La Nina event. in our models, and the way we did that, instead of using like your standard new 3.4 box that everybody does, the issue is that your CMIP6 model not necessarily have the variability at the right location as your new 3.4 in observations. So what we did, we defined a custom box, and where you have the highest variability of this SST in the tropical Pacific. And then we define our El Niño events and La Niña events as a 0.75 standard deviation threshold of those SST anomalies. So each model will have their custom box based on their pre-industrial runs. I'm sorry, the historical ones. And then that's how we define the El Niño and La Niña events. Okay. So now we know which models have a lot of diversity, little diversity, and now we define our El Niño and La Niña events, so we can do what we do with large scale stuff. We can do composites. So this is the one of the Genesis index that we do a lot, and this is the same one that Adam was talking about, and these are composites. Or on the left, we have 45 models that I'm working with, and this is El Niño minus La Niña Genesis index, and you have, the reduction of tropical cyclone activity in the Atlantic, increase in the Central Pacific, and near Asia you have the decrease. You have this dipole in the Southern Hemisphere. This is your typical, if you look at reanalysis and stuff like that, you can get the same thing. Now, if I look in the future, and now I have always three category of models. We have your A+ models, A and B models. Seems that, they all seem to be more or less the same, similar patterns, with the B models composites seem a little weaker. Okay, so far so good. This is all historical stuff. Now let's look at the end of the century, now getting SSP 585. So you strong, strong scenario that maybe we don't believe it's going to happen at the end of the century, so that we get the strongest signal that we can. And then if we put all models together and we do the, you see this pattern is very similar to observations. And then in the different models, now we start to see some difference in the future. If I now do the difference between the El Niño minus La Niña pattern in the future minus El Niño minus La Niña pattern in the historical, then you start having difference. So now what we're seeing is that the models that have this tendency to do too much Enso diversity, the pattern of your El Niño minus La Niña in the future is changing compared to the historical. While the other two type of models, they are basically having the same pattern with some strengthening or decrease in some specific region. But this is the one that really gets our attention, that the pattern is really changing. So these Genesis index are composed of different environmental variables, thermodynamical variables, dynamical variables. So we want to see, can we say if this is a thermodynamical thing or a dynamical thing, where it's coming from? So for instance, let's look at your potential intensity, which is very similar to SST, which is part of the Genesis index. And then here your El Niño composites in the historical for El Niño minus La Niña composites in the potential intensity, which is similar to what you get at SST. Now, if I do the same, and the difference of El Niño and La Niña composites in the future and in the present, then you start to see that we really have the patterns of the El Niño minus La Niña is really changing for these A+ models in a way that the A and B models are not doing at all. So if you have your model, doing too many Central Pacific events, then we end up having this relationship of Enso tropical cyclones change in the future. that's not the case when you have the right diversity or even weak diversity. So this is the thermodynamical variable is doing that, and then we can do the same with the vertical shear. And then here, I forgot to say, all this composite in August, September, October in the northern hemisphere, January, February, March in the southern hemisphere, so that we have the peak season each hemisphere for tropical cyclones. And then we see here, you know, the same patterns more or less in the historical for all types of models, with stronger anomalies for the A+ models than the B models. But then again, the vertical shear patterns between the future and the historical are also changing for the vertical shear. So we also have dynamical changes in these models that have, you know, are overdoing your Central Pacific on new events. And we have weaker anomalies in the other ones, but the same type of anomalies that we have in the historical. Okay, Adam just went through this. So this is what we're saying, that, you know, the trends in the equatorial Pacific are also, you know, the historical, and the models are wrong, and then we have they're typically going towards more El Nino type trends in the future. So the question we have is there, can we say, is there a relationship between the models that are doing a lot of Central Pacific events and this trend in the Pacific or not? So this is the same type of plots that Adam has shown. So now we have 45 models, and then we have your A+ models, A models, and B models. So this here the observation, more La Nina type of trends, and here, you know, the same story that show that, you know, a lot of the models have more El Nino-like trends. But what's interesting is that now the models that have the weak diversity, their east-west gradient is basically really concentrated towards 0. And you have, you know, seems, you know, at least the A+ models that have a lot of Central Pacific has more accentuated these El Nino trends in the future. So we have to understand this better, I think, for our paper. So I'll conclude here. So this, at least in the large scale environmental fields that are associated with tropical cyclone activity, we see a difference on the ensotropical cyclone modulation in the future, depending on how well your model is simulating ENSO. So this is really coming for the ENSO part, not the tropical cyclone part, because here I'm just looking at large scale environmental fields. If you have changes in the ensotropical cyclone modulation in the future for these models that overdo the Central Pacific El Nino, compared with the ones that don't. And these different patterns are present both in the thermodynamical and dynamical fields. And also they have some relation with the trends in the Pacific. Thank you.
I'll go deep into the weeds immediately, I think. If you go all the way back to your bar plot, that shows all the A+, the A, and the B models. I was unfortunately reading the labels, and I think in the A+ models, there's CESM2 FB2, a low resolution version of CESM2, and I think CESM2 Wacom is there, yeah. Oh, also 2 degrees. So and then
it's all CMIP 6 model.
Yeah, and then CESM2, the 1 degree version of the same model, but with a lower top atmosphere, is an A model. And I'm wondering if you have any clue, like within the same kind of modeling system, is it like among those models, is horizontal resolution in the atmosphere important, or is it the having a stratosphere, but I guess not, or having chemistry, but I guess not? So is it just horizontal resolution?
I think we would have to run some simulations to figure that out, right? It's, you know exactly what you're saying, get your MCAR model and run with high resolution, high top, low top, and try to test that. I don't think just by looking at the six simulations, we can do that. I don't think the sample is big enough to ask this question, to answer to your question. You can plan some experiments together.
You, the questions? So, yeah, you analyze the ENSO relation. ENSO is of course the most biggest mode. So do you think any other mode important for the TC projection?
Oh, yes, I think we should be looking at this in other climate modes that are important for cyclones as well. AMM, all the other things that we talk about. We start to answer with the big elephant. Especially because we also have this issue of the trends in the Pacific. So that's in the Pacific, it's really going to be determining a lot what's going on.
See. So, yeah, for example, last year, yeah, it's a kind of a El Nino. But the very unusual in the Western North Pacific, very few tropical cyclones.
Yes.
So, yeah, we are still trying to understand. You saw something with last year's behavior?
Yeah, so while there is a relationship of Pacific, it's, you know, at least our work from some years ago is a strong relationship in terms of intensity and the tracks. But really, I submitted to I do write the summer of the Western Pacific for bands every year, and I just submitted my summary, and basically we're saying, yes, it was an El Nino event, and the Western Pacific really behaved different, and it's not clear exactly why it did that. You did have a lot of intense cyclones.
Very few cyclones.
Very few, but you have a few intense ones.
Yeah, in some area.
Yes, so like one of the statistics that I do is the ratio of super typhoons and typhoons to number of storms. And those, you know, the intensity, which is a measure of how many intensify, and those were more similar to El Nino time. But because the number was so low, we didn't have that type. It was, you know, overall the season was not typical for El Nino ACE or anything like that. Yeah, so the ACE was actually very close to average for the whole season, while the other measures of number were very low. But in terms of like number of super typhoons, actually was average. So it was a mixed match in terms of, depends on which diagnostic you use to characterize this typhoon season last year.
Thank you very much. I think that the impact of ENSO on tropical cyclone activity is related to the local circulation and Hadley circulation change. And you mentioned that you saw the change in the vertical shear, and I think such large scale vertical circulation is also important. And what do you think about the A plus category, the change in the Walker and Hadley circulation?
Yeah, actually, Chang has done some figures showing the changes in the Walker circulation in some of the models. So I just didn't show because she was probably going to show that.
Okay. Thank you very much.
Thank you.
Okay, thank you. Next, Kevin Reed.
Wow, smoothest transition yet. All right, so yeah, my name is Kevin Reed. I'm at Stony Brook University. I'm gonna spend a little bit of time talking about approaches to storylines, particularly within the community Earth system model for quantifying climate impacts on hurricanes. And so I think it's kind of a nice topic to discuss because we've heard about storylines a few times in the discussion and also in Pierre Luigi's presentation earlier. But before I jump into storylines, let me focus quickly on what I refer to as the traditional approach. So I know that a lot of the focus on some of the presentations thus far has been on storm genesis, frequency, and location. But there's been a variety of work that's kind of focused on the hazard side of the storms, right? So trying to understand, for example, where hurricane rainfall will change or how it will change in the future. And so one of the traditional ways to do this is to run a present day simulation with a high resolution climate model similar to those that are done with high res MIP that Pierre Luigi had mentioned, as well as we've seen in a few of the other talks. And to run a variety of ensembles to start to look at tropical cyclone rainfall. So I'm going to go over this pretty quick because I'm going to jump to, there we go. So one of the ways in which we've done this in our group is we've looked at, this is a historical AMIP run. This is just number of storm hours. And so this is similar to a frequency, right? But it's only overland. So how many hours of impact per year come from a hurricane? And this is through a multi-member ensemble of the same model. And one of the things that we've been able to do is try to quantify rainfall from those storms. And so this is a way in which we've used tempest extremes to extract hurricane-specific rainfall. And then in doing so, if you take the middle column and divide it by the left column, you get what is the rainfall per hour. And so we've done a lot of work looking in these simulations to say how well do they represent the observed rainfall from hurricanes, as well as this is maybe a way to think about intensity, average intensity. And what's interesting is when you look over a variety of ensembles, the model can do quite reasonable at getting the amount of rainfall from storms. Now, and I'm not showing that, so you'll have to trust me on this, and you can look at Alyssa's paper at the bottom. But one of the interesting things about this is that even if the model doesn't capture the number of storm hours right, so it has a bias in its frequency or maybe where the storms go, it actually does capture the characteristics of rainfall and rainfall per hour correctly. Which means if you kind of look past some of the biases and maybe where the storms go or genesis locations, then you can start to look at these future scenarios. And so this is just for an RCP 4.5 and an RCP 8.5. And this just starts to show how you can use the conventional approach to tease out, okay, so similar to some of the work we've already seen or some of the results we've discussed so far, is that maybe that across large parts of the United States, there's a decrease in the frequency or the storm hours of hurricanes in the future. But if you start to look at rainfall and the amount of rainfall per hour, here is where you start to see an interesting, that very clear climate signal. So I think Adam even put this on one of his slides from the IPCC, is that one of the clearest aspects of future projections and tropical cyclones, that the amount of rain per hour of impact is increasing. Right, so if you take this and you have a traditional approach that suggests, okay, if you run a climate model and you run ensembles of it, so you blow through millions of core hours, you can get this kind of a simple, right, finding that the amount of rainfall per hour of impact is increasing from tropical cyclones. So how do you start to translate this, right, to better understand risk in the future or to better communicate with stakeholders, including the public and decision makers? And so what I'm going to focus on for the motivation and talk about the storyline approach here for the remainder of the talk is to say, one of the early questions we had is, could we find this impact in the climate models? Could we actually find a climate change impact in both past or future climate change in this case, and I'll show both, in rainfall associated with specific individual storms that have actually recently occurred or whole hurricane season? So can you actually quantify this signal in recent storms? And this helps to kind of maybe look at the second question, which is, can you then use such frameworks to better translate the impacts of climate change to the public decision makers? And the idea is that, yeah, we can talk about risk and changing in probabilities of storms making landfall, but can we use specific storms of record to help communicate climate risk through that? So changes in the hazards of them storms themselves. And so I'll focus on rainfall I motivated with that first slide here. So what is the storyline? So really quick, the simplest way, don't even read all the writing on this slide, and just know that a storyline approach is just taking your climate model and treating it as a weather model. And so instead of focusing on long-term simulations, you're just initializing the climate model at specific times in advance of storms of interest. And then you're running a 7-day forecast, just like you would an operational global forecast model. And so there's advantages to this, in part because you can use the same climate model that you've actually developed climate signals with, right? So you're doing everything within one approach. And so just a little bit more detail of how we specifically do it. So I'm going to focus everything here on NCAR's CESM, but we've done similar things with the Department of Energy's E3SM. Because we're focused on hurricanes in the North Atlantic, we make particular use of the variable resolution capabilities of the climate model. So we run with a high resolution nest over the North Atlantic. In this case, our high resolution is taken to be 25 kilometers, which is kind of conventional for high resolution climate modeling within CESM. But this can go down to 14 kilometers and beyond, which is active work. And we create, for the storyline approach, we create two sets of simulations. One in which we call an actual. And this is, again, no different than running the climate model in AMIT mode, which is with prescribed SSTs. But instead of just initializing randomly on January 1st, 1979, and like in the AMIT protocol, you initialize at a specific date in advance of the storm of interest. Now, because there are some data assimilation capabilities within CESM, but we are actually outsourcing our data assimilation. So we're just taking the operational input that goes into the NOAA global forecast system and initializing our model with that. And so, right, so that it's initialized both the 3D, the 3D atmosphere, the boundary conditions are all initialized with NOAA GFS initial conditions. And then we also create a set of counterfactual simulations. These are and so for this talk, I'm focusing on the thermodynamic impact of climate change. So we adjust the 3D temperature structure, specific humidity, sea surface temperature, and of course, if you adjust humidity, you have to adjust surface pressure of those observed initial conditions and boundary conditions. So essentially all we do is we take the NOAA initial conditions and we adjust them to remove or add large-scale climate change signals. And the advantage here is that we can calculate those large-scale climate change signals from the CESM model itself. So it's run a variety of simulations, both for the large ensemble or for the C20C plus effort, which is a detection and attribution effort in which you have a world with and without climate change. And you can create this large initial perturbation essentially to your actual simulations. And so the advantage here is that if this is done and if it's fit for purpose, which I'll talk about in a minute, you can actually compare the actual to the counterfactual forecast, and you can start to look at things like changes in structure or intensity of the storm. What you can't do, of course, is related to the conversation that we were just having towards the end of Adam's talk, which is you can't say anything about the probability of the storm. So in all cases here, the probability of the storm that we're exploring is 1, right? So the storm is in the initial conditions, and we're looking at how it evolves in a slightly perturbed climate state. And so it's just really quick, right? So I've spent 2 minutes explaining to you that these are essentially pseudo-global warming-like simulations. The main difference is that we aren't using a regional climate model that has a totally different dynamics and physical parameterizations. We're using a consistently one climate model for both the climate change fingerprints as well as the simulations. The way in which we do this is actually way more complicated than you think it might be. And so we make use of what's called BetaCast. This is essentially a wrapper that goes around CESM in order to initialize all the different components of the model needed at specific times. And so actually it's a wrapper that pulls over operational data directly from NOAA to run these hindcasts. And so there are folks like Colin Zarzicki, which I think is speaking a little bit remotely later, in which you can actually do these type of things operationally. And I will actually show an example of that towards the end. So really quick, one of the ways in which we can build these counterfactuals is we can make use of the CESM large ensemble, which is a 40-member ensemble that has first an 1850 control of over 1400 years. And then you have simulations, starting in 1920, initial perturbations that run off into actually the end of the century. and with 40-member ensembles. And so what we are able to do is we can actually pick a month of interest. So if we're looking at a storm in September of 2022 or 2017, whatever it might be, we can actually average the September atmospheric state from these 40-member ensembles, and we can compare it to the 1850 or pi control run that's typically right in the CMIP convention, and you can calculate the large scale thermodynamic signal. You can do the same as if you want to compare a storm in a specific time to in the future in a warmer world, which I'll talk about towards the end as well. You can do the same thing in which you can create these large scale perturbations that are calculated right from the CESM large ensemble itself. And here's just an example of what this looks like for 1 month. I think it's 2020, September 2020, and this is the large scale climate change signal that you get when you do this type of analysis. And so you can see it's relatively smooth, in part because these are a 40-member ensemble. But there is details, right? That's the fingerprint part of the warming. That the warming, of course, isn't equal across all of the ocean. Yeah. And so this is essentially the perturbation that we can add and remove, for example, from our counterfactuals. Or from our actuals for our counterfactuals. So I'm just going to walk through some examples of how we've done this, and then I'll finish up with some of our future work. So one of the first cases in which we did this was for Hurricane Florence in 2018. The Hurricane Florence dumped almost 3 feet of rainfall in parts of the Carolinas. Right, so almost a meter of rain. And one of the first things we do is we can run, the nice thing about these simulations is they're cheap, they're 7-day runs, so we can run 100 ensemble members. And so here's an example of the actual in red and the counterfactual. And so here the counterfactual, the next few slides are attribution-like storylines. So they're looking at the warming to date, what has the role of the warming over the last 170 years been on the storm of interest. And the nice thing to notice is that if you compare the tracks between the actual and counterfactual, that they're very similar. So adjusting the large scale thermodynamic state hasn't adjusted the storm's track. Now, of course, if you compare to the black line, which is observations, of course, the model is imperfect 3 days out of landfall. And if I was to plot all the operational tracks at forecasted tracks at this initialization time, they would also have a very similar bias. But what's interesting is the model is actually able to capture the location of landfall within 30 kilometers. So 98 of the 100 ensembles come within a very narrow range of the observed landfall. And this means that what we suggest that the model is fit for purpose. In part, it can do reasonable, it can do just as well right to the operational models, which we could talk about how we quantify that. But also it can capture the landfall location reasonably well. And the tracks aren't that different between the actual and counterfactual, which means you can just compare them as apples to apples, right? So one of the ways in which we do that is we look at rainfall. So the observed rainfall is on the left. You can see there's parts where it's over 30 inches over the course of the storm. And then the middle is the actual. The middle is 98 ensembles average, so it's an ensemble average. So of course it's way smoother than the observed, which is one reality. But also you can notice here's the impact of the slight difference in the track, right? Is that the rainfall maximum and pattern is slightly different. But it's able to capture those large rainfall amounts that have occurred in reality. And then if you compare it to a counterfactual in which the large scale climate change signal to date had been removed from the initial and boundary conditions, you can see that while the rain distribution looks quite similar, that the amount of rainfall has decreased. And if you calculate it, it's actually that in the counterfactual, the rainfall has decreased by 5%, or you could say that in the actual simulation that the rainfall had increased by 5% because of the climate change signal. And so that's one way. That was our first storm in which we did this, is what we call our prototype approach. And then more recently, we explored, could we do this through an entire hurricane season by operationalizing it? And what I mean by that is that we just initialized for all of the 2020 hurricane season, started June 1st, all the way through November 30th, every 3 days. And since this was just an initial test, we did it every 3 days at 0Z, we initialized the model. And so we've come up with a season's worth of counterfactual and actuals for a variety of storms. We can, again, calculate the rainfall that's associated just with those tropical cyclones. And then we can kind of look at the statistics across all of the storms. So here's just an example. This is for 3-hourly rainfall amounts, right? So this is kind of similar to that rainfall per hour of impact that I showed you in the traditional approach. And you can look at the change in the probability of specific rainfall rates. And what you can see is that if you focus just on the total distribution, you should see that there's a shift in an increase in probability in the most extreme rates. And if you look at the 99th percentile rates within the whole season, that we see a shift of about 10%. And so that suggests that not only are we seeing an increase in the intensity, or sorry, the accumulated amounts, that if you actually, that those increases is coming through changes in the rainfall rates. And we've also looked at accumulation, which I'm not showing here for this 2020 season as well. And so what we're starting to see is that in both of these cases, we've had about a degree warming, right, in the observed record, degree Celsius. The North Atlantic is a little bit cooler in terms of its warming amount. But in this case, we're seeing already a detectable, at least in this approach, a detectable change in the rainfall amounts, rates, and accumulations within these storms. And so this is just one way, and we can start to translate, right, the impact from the traditional approach. And now we have actual individual events. We have a season, for example, in which you can start to communicate the actual risk of climate change through these discrete events that have occurred or events of record. So recently we've started to deploy this in real time. So here's an example for Hurricane Ian, in which we ran the storyline framework in advance of Ian making landfall. So in reality, so not just initializing the model, like we initialized the model 2 days before Ian made landfall. And we did this analysis. And so here we focused on just changes in the accumulated rainfall amounts over land. And you can see, or actually in this case, it's everywhere. You can see that the increase in accumulated rainfall, for the probability had increased of certain amounts by over 18%. So this is just showing that we can operationalize this, and we actually put a tweet out, or X, or whatever it's called now, in which we were able to communicate this while the storm was happening, right? That climate change had impacted this storm. And of course, it's worth mentioning that we're able to do that because we had published the approach multiple times with different storms in the whole season. And we're using a climate model that had been using to explore tropical cyclones for over a decade. And so we kind of understand the limitations and the strengths of the model. And so the approach here is that actually, since it's no different than a weather forecast, you can actually start to do these type of things in real time. And so I just want to finish with an example of, so thus far our work had focused on exploring counterfactuals that were the warming to date. And that can be a useful tool for the communication of the risk of climate change and how it's changing storms now. But also kind of related to some of the themes of the discussion so far this morning is that we can turn that around. Instead of trying to look at the warming that's occurred to date, we can look at the warming in the future. So we can use the CESM large ensemble for the same thing, in which we can identify times in which the world is on average 2 degrees warmer, 3 degrees warmer, or 4 degrees warmer from the surface temperature from pre-industrial. And we can actually add the delta to the initial condition as opposed to removing it. And so this is some work from a recent undergraduate student, Annika, who worked in my group 2 summers ago now, in which we had run a set of storyline simulations with Hurricane Irma, in which we ran with these the present day and then a 1, a 2, or sorry, a 2, a 3, a 4 degree warmer cases. And so this is just an example of how you can start to build out this framework a little bit more in detail. And so you can run in initial conditions in advance of when the storm made landfall, and Hurricane Irma in this case. And you can identify what initial conditions, what initialization time, for example, forecasts the track the best. And that's what's kind of being shown over here, which is track error. And then you can identify, okay, so here's an example of, right, the 990Z1 has relatively track errors for multiple days. And so you can use this one as the one you want to perform your analysis on. In part because when you have storms like Irma, in which they have like a slight perturbation in the track, could mean whether it's out over the ocean or over land because of the way in which it made landfall somewhat parallel to the coast. It's important to do this type of kind of identify which of the initializations are ideal, but also you want not a lot of variability in the track with the different warming perturbations. So that's additional requirement. And so here's just an example of what you can see if you look at changes in observed rainfall to the present. as well as looking into the future, you can see that even in this case, we see, right, for each degree of warming, we see a significant increase in the mean precipitation, the mean rates, the max rates and accumulations. This is accumulated. But we can start to build a analysis like this, which is looking at different rainfall percentiles in terms of rates. We can look at what's the climate change signal on these. And so, right, I guess the yellowish color is a 2-degree warmer world, all the way up to the red, which is a 4-degree warmer world. And what we can see is, of course, that at higher or at more extreme rainfall rates, the change in per degree Kelvin is actually increasing. And so this is just another way to show that, right, if you look at this storyline perspective from looking into the future, you can see that you can start to use this as a tool to look at the change in not only rainfall rates, but also accumulations that I showed on the previous slide. So some of the main takeaways I just want to finish up real quick is that the storyline approach does suggest a consistent conclusion with those conventional climate simulations that I started at the top, which is the amount of rainfall per hour of storm impact is increasing and will increase into the future. And that there's a growing effort by those in the scientific community to try to work directly with stakeholders. And so this storyline approach and the way in which we've started to do this actually has come directly from working with water resource managers in Florida, for example. I'm going to give an example of how it's taking a turn by working with them. And so I think the storylines are a promising approach for this type of interaction. So I think it's one component of maybe what Adam was arguing for earlier. But it also does suggest that there's a pathway to operationalize storyline frameworks. Most storyline frameworks to date have focused on the developed world and storms in the developed world. And if you operationalize them, you could actually, you could have these every day for everywhere around the world. So just to finish up with a couple examples of some of our ongoing work. So one of the ongoing work, right, is that this is the Irma work I just talked about. But now we're in the process of not focusing on the tracks that were well simulated, but focused on the tracks that were not well simulated. And the idea is that these are plausible scenarios in the future for a storm. And so here's just an example of it where you can see that at earlier initialization times, and you might remember from during the time in which Hurricane Irma was happening, that there was some fear early on that the storm was going to make landfall right into Miami. And so you could actually, by talking with water resource managers, when we showed them this, they're like, oh, all this work you've done is great, but could you analyze this orange track for us? Because that's what we're interested in. And so we're in the process of kind of doing the same approach of looking under different warming levels by focusing on plausible paths that were predicted a few days earlier, but didn't end up happening. And so it's a way to kind of provide potential scenarios under climate change for our stakeholders. And of course, it's noting that, right, we can't say anything about the probability of that track being more likely than the other, at least with this approach, but it allows us to kind of use the next storm of record and say what happens if that forecast would have been the right one. And then we are, and Tianyi is going to show this in his talk tomorrow, but as part of the hurricane project, we are looking at this now in using different types of storm, focusing on those storms that are undergoing extratropical interactions and looking at these thermodynamic impacts. And this is an early slide that I stole from Tianyi's update a few months back, but is it just a way to kind of say that we've focused, of course, so far on the storyline of focusing on storms that have made impact on land, but you can do the same analysis for scientific reasons and trying to understand how is these type of storyline simulations used for looking at those extratropical interactions that Pierluigi had mentioned. So with that, I will finish and there's some time for questions.
Hi, thank you. I'm just wondering from a methodology perspective that the fact that you're using the CESM model with a variable resolution, does that somewhat negate the advantages of like using the climate change counterfactuals that come from the CESM model and that model's physics being the same as the operational model?
Yeah, so that's a really good and important question. So there is an initial, like for any initial conditions of any, right? So anytime you run the model, there is an initial spin up process. And so we account for that in the beta gas framework in which we can deal with some of the facts that it's not a completely balanced state initially. And so we have ways to account for that, whether it's filtering out gravity waves, or whether it's actually doing a kind of a hydrostatic balance before we initialize the model. And so that's one of the things that we have to adjust for, in part because the initial conditions are coming from a different model than, right, the large scale force fields. So we do account for that, and that of course is one uncertainty. Now I think the other point that you're making, right, which is that the resolution of the variable resolution component is much higher than that conventional version. And so there's been a variety of work to suggest that at least within CESM with some of the physics packages, that there's a large, in any model, there's a sensitivity in the parameterizations to grid resolution, of course. But when you look at the large scale kind of climate within a region, that it's not so terribly impacted by it. So you'll get some local scale changes. Now, the other thing that's one of the advantages to running with in this weather mode is that oftentimes we're only running for 7 days. And actually what I did, most of the time we're doing the comparison in days 3, 4, 5. And so while some biases in the model will spin up quickly, a lot of the kind of large scale biases are in the initial conditions, the initial conditions are initialized and relatively well balanced. And so you don't have too much of an issue. But I think it would be important to kind of get around some of the uncertainty that you're, I think, alluding to, which is is either exploring using different models to calculate the climate signal, right, to ensure that what we're seeing is consistent. And there's ways to do this utilizing the CMIP-6 archive, of course. But also to try to do similar approaches in different models and to see. I do want to just add, though, that I'm fairly confident that the percentage changes that we see here are actually conservative, right? Because actually the large scale climate change signal to date isn't a smoothed out field of 40 ensemble members. And so in reality, it's possible that these estimates are actually inherently conservative, and that in some cases they might actually.
Just may I ask what's the resolution of the tropical cyclone simulations?
Yeah, so right now we utilize 25 kilometers, which is what we've been doing with CESM for over a decade. And so it's able to produce not only the rainfall amounts and rates, as I had shown reasonably well, and I didn't show much of it, but we've done a lot of analysis to show that. Also, some work that we've done in the past shows that it can get reasonably well at intensity and the kind of relationship between, of course, surface pressure and wind speed, but also even size is actually remarkably well resolved, outer size.
You show the variable resolution model configuration.
Yeah, so the variable resolution, the high resolution domain is 25 kilometers, and the outer resolution is 100.
I wonder, Kevin, what's the biggest confusion or pushback that you get from stakeholders? Like you mentioned, the water resource managers, are they pretty tapped into this, or is there a lot of confusion? What's that process been like?
Yeah, so like any stakeholder engagement, I would say that we've learned. I should mention that we're in year 8 of this project with them, and so that's taken that long to the point in which we're really starting to iterate on how we do our science. In ways in which we're advancing the science, and of course, not just being completely responsive to what they need. And so I think that one of the examples is the metrics, some of the actual rainfall metrics that we use are things that we've learned from them that are useful for their needs.
Yeah.
And they aren't necessarily ones that we would use, right, in scientifically. So that's been one of the things. In terms of what we've learned from the storyline framework, is one of the downsides of the storyline framework. You focus all this analysis on one storm, and then that's great for your stakeholders that are in Tampa Bay, but your stakeholders over here in Miami, right? So that's how we've gotten to the point of, okay, can you build these worst case approaches or these probable storylines that didn't occur? And so that's one of the ways in which we adjusted. So some of the early work was around metrics development. What are the metrics that we're going to use? Now, oftentimes, what we publish in a paper isn't the thing that's the most particularly interesting to the stakeholder, and it's through the engagement and learning how to define their own approaches and their own models and how to ingest climate data into it. It's something that doesn't get scientifically, put in a paper, but it's part of the process of work. Thanks.
Any other questions?
I guess this is related. So is the focus on rain because of the stakeholders,
Yeah,
Or is it because you're not happy with the winds in the model?
Yeah,
or-
no.
Or have you done the wind? and you
Yeah.
switched on- or-
yeah, so great question. So the focus on the rain is in part because early work was funded by the Department of Energy, who was very interested in understanding where water will be in the future. And so our stakeholders early on in developing the framework were water resource managers across the country, but we focused on Florida. And so that was a focus on the rain. The other reason is that we've shown through a variety of work that despite the resolution constraints, that the model actually does a really reasonable job at rainfall amount. And of course, if you look at wind speeds at the lowermost model level, right? I mean, it's not going to do as well as it's doing at rainfall, in part because you need to go to higher resolutions, as I think, Pierre Luigi was showing, in order to capture the wind speeds. But if you look at things like surface pressure, then the model, again, even at these resolutions, does quite well. And so, one of the aspects is, a lot of our thinking about tropical cyclones depends upon wind speeds and intensity from that perspective. And it's actually one of the things that most models, including operational models, aren't particularly good at. Okay.
Thanks. So this is actually a comment rather than a question. If you go back to the Florence stuff, and it's just because we're in this room and Sandy happened here. So the track of Florence was particularly zonal.
Yeah.
And I was just down in North Carolina last fall talking with Rick Lutic about this and the flooding that it caused. And you're right, like the forecast got it wrong 5 days out. And then what happened was a high pressure system showed up, and similar to the turning that happened to Sandy happened for Florence. And just because we're in New York right now, I just wanted to point it out.
Yeah, well, I think since you brought it up, let me comment on a couple things, which is first, while the model doesn't capture multiple days out the turn, if you initialize sooner, it will. And second of all, one of the important things that it does to get the rainfall amounts right, though, is it at least captures the slowdown. So it's hard to see with these black dots here, but it captures the slowdown near landfall. So that's also an advantage to some extent. And also one of the advantages over using a global model for these type of runs than a regional model, which might not capture some of that slowdown due to the setup or issues with lateral boundary conditions. But in terms of, your point brings up the opportunity where we can start to bridge that gap. And I think it goes back to the question that maybe Pierre Luigi had after Adam's talk, or maybe it was Philip, I don't remember. But there was a talk that kind of started, storylines can't be the only way to assess risk, but maybe you can start to use storylines to start to think, okay, can we start to look at, the conditions that lead to that type of track? And can that be one way to bring some probabilistic analysis into the storyline framework? And you won't ever be able to focus, okay, on this one specific region, but could you start to say, and we know that storms, that set up with these conditions that have this unique kind of zonal track, are likely to occur more or less or whatever it is. And you can start to build, I think, probabilistic information on top of your storylines.
Okay. Okay, it's almost time. Thank you very much. Thank you very much. I want to close the morning session because it's people are viewing online. But this is the first session is only the distributed online. But thank you for all the keynote speakers, and thank you for the audience on the online and in person. But the good news is you can still continue connected Zoom. So 3 days we plan to distribute in the world. So your colleagues may connect to join the conference. But please come back 1:30 in this time zone. So thank you very much anyway. So please enjoy the lunch. Thank you.